so we're gonna talk about recrystallization, and let's do like from the very top down. Why is it that we do recrystallization? What's the point of a recrystallization? When would you consider doing it? When would you consider a recrystallization? I can edit out as many seconds as you want away. Why am I talking about recrystallization today?
It's like when like a solid can come out of a solution, but then you can...
Well, I understand that, but I'm saying why would you even consider doing this thing with the solids and the liquids and the heating and the...
To purify.
To purify, right. So recrystallization is a purification technique. And what kinds of compounds does recrystallization work for? What kinds of compounds can you do a recrystallization on?
Ones with a melting point lower than room temperature.
So ones with a melting point that is lower than room temperature. So you're making an assumption that the thing is a solid, right, at room temperature. Yeah, you have to have a solid in order to recrystallize. So that's sort of step one. So if your product of interest is a solid, then recrystallization is a possible technique. Typically, recrystallization as a purification technique works best if it's a reasonably pure solid, meaning the level of impurity is relatively low. So you want a relatively pure, solid material, and we'll explain why that's the case in just a second. So let's talk a little bit about the theory of recrystallization. So in recrystallization, you start with a crude material. Okay, so actually I'm going to erase the solvent for a second. You start with a crude material, and let's say we're doing a reaction where we generate a molecule A, and it has some impurity B in it. And see, these are just generalities. So initially what we do is we pile up the crude material into a Erlenmeyer flask. Erlenmeyer flasks are the desired flasks to do recrystallization because evaporation is slow from them. And the first thing that we do is we make a saturated solution of that mixture of A and B in some solvent. So if we kind of looked at the microscopic level, we would have lots of A's and a few B's floating around. And what's it mean to be a saturated solution or a supersaturated solution? How do you get a solution of that kind? What do you have to do? What does it mean to be supersaturated when something's supersaturated?
You have to heat it.
Yeah, so why do you heat it?
So that like the interactions of like the solvent and the solvent are like maximized, I guess?
Yeah, so the interactions between the solute and the solvent are good and strong, but the general trend that we're looking for is that things tend to be more soluble when the solution is warmer, right? So the warmer the solution, the more soluble something is. So if you add a solid to a boiling liquid, and you add enough solid so that no more can be added without it sort of remaining solid, right? So it's dissolving, it's dissolving, it's dissolving, and you add a little bit more solid, and it can no longer dissolve. That solution is totally saturated at boiling temperature, right? So then you could add just a little more solvent to dissolve that, and you have a solution of that compound that is saturated at a higher temperature. And then what you can do if you want crystals to form is you can just take that solution off the hot plate and let it slowly cool. And the solubility of those compounds as the solution cools goes down, right? And reason tells us that if you had a solution like this with A's and B's and a lot more A's than B's, the thing that is more concentrated will come out first as you're cooling because there's a lot more of it, so its concentration is higher. So as the temperature gets lower and lower, the thing that's in higher concentration tends to, not always, tends to drop out first. And so, we're doing a chemical reaction, we generate a lot of A and a little side product B. When you've got this supersaturated solution, and I'm going to show sort of, steam coming off the top, like vapor coming off the top because it's boiling, right? And you let the temperature decrease when you remove it from the hot plate, what's going to happen is you're going to start to form crystals of that A molecule first, and the hope is that you get a more dilute solution of A and B above the top, and these are still in solution, and A is all clumped at the bottom, right? And let's say this is the situation when it gets down to room temperature after you let it slowly cool. Crystal formation tends to prefer taking molecules that are the same and making crystals out of them. So the interactions between A and A allow this pure A crystal to form and excludes B from that crystal. Okay, and so the idea is that now we have a solution of A and B. There's a little bit of A left, and there's hopefully all of that impurity B. And then we have solid A at the bottom. Now what we can do is break up those crystals and now do a filtration, right? Because these are in solution, we'll pour those right through the filter, and we'll end up trapping crystals of pure A. You can't avoid losing a little bit of A, because it's going to be maybe a little bit soluble at room temperature, hopefully not too soluble, and hopefully all of B is soluble at room temperature. If its concentration is low, that's likely, right? That's the reason why a recrystallization works best when you have a very disproportionate reaction mixture, where the thing of interest is the thing that's in highest concentration, right? Because what you end up with always is a dilute solution of the desired thing plus all the impurities. Does that make sense? Okay? So that's the theory. So in the lab, I want to talk about how this is actually done. So there are a few things about the actual practice of recrystallization. Okay? The first thing you have to think about with recrystallization is what solvent are you going to use? So let's think for a second about what characteristics would be good for a solvent for recrystallization. What characteristics would be good? Do you want a solvent that your compound just readily dissolves in super easily? Peyton, you're kind of explain your head shake.
Because then it's a lot harder for it to stay recrystallized.
Yeah, so at room temperature, if the stuff is super soluble at room temperature, you're not likely to get crystals. Or another way of thinking about it, if it's super soluble, this concentration is going to be relatively high. Even if you get some solid out, there's still going to be a lot of the desired stuff in the solution, so you're going to waste a lot. So what is the property of the solvent, the ideal solvent for recrystallization? What would be a perfect solvent for recrystallization for a given compound? What would be the perfect characteristics?
Soluble at a reasonably high temperature.
Something that has differential solubility at different temperatures, right? So the first thing you would want to check is that at room temperature it's not super soluble. And then you would want to see what happens if you warm it up. And if it goes into solution, ooh, that's a good candidate solvent, right? And oftentimes at the beginning of a recrystallization, that's exactly what you do. The way I like to do this protocol is I like to get an evaporating dish like this. And I like to put a crystal of the compound or some of the solid in the middle, just a little bit, just a tiny bit. And then I take 1 or 2 drops of different organic solvents and I drop them on. If they instantly dissolve, that solvent's out. It's not going to work. That's at room temperature. If it instantly dissolves, that's not a good solvent. So then, once I find a solvent that I add at room temperature, and it doesn't immediately dissolve, or it takes a long time to dissolve, it's only slightly soluble, that's a good candidate, right? And then what you can do is you can take a little heat gun, or even your finger, or maybe on a hot plate or something, and warm it up just a little bit and see if it goes in, right? And if it goes in at high temperature, but then it drops out at low temperature, that's the perfect solvent, right? So initially the first test is make sure it's not super soluble right at room temperature. Acetone is a fantastic solvent. It dissolves lots of things, but that's not necessarily good for recrystallization. You want it to be slightly soluble at room temperature, right? So I've asked Carolyn to set out an array of solvents for you to try if you want to do recrystallization. And you can always ask us for more. We have lots of solvents in the stockroom. And so, you know, you should, if you get a solid after your reaction mixture cools, you can take some of that solid and test different potential solvents. Ethanol and methanol are really good recrystallization solvents for a lot of organic molecules because they're fairly polar, and the non-polar organic molecules are sometimes insoluble at room temperature, but as you warm them up, they become soluble. So those are good choices, and things like toluene is available, has a very different set of intermolecular forces that it uses to dissolve compounds, right? Ethyl acetate, acetone can be used for some compounds. So dichloromethane tends to be a fantastic solvent, but for some compounds they'll only be slightly soluble at room temperature, right? So think about solvents that are available to you and test them until you find one that you think works. Sometimes it will turn out that you can't find any solvent that has that property, right? That at low temperatures it's insoluble and at warmer temperatures it's soluble. And sometimes what you have to do is you actually have to make a mixture. You take one solvent that it's really insoluble in at all times and one solvent that it's really soluble in at all times, and you make a mixture of those two, right, in some proportion. That is now beyond a simple recrystallization. Now you're actually having to fine-tune a solvent mixture, kind of like you do for TLC. Okay, so that's something that you can also do if you can't find a perfect solvent. So then let's imagine that you have the perfect solvent picked out. Let's just talk a little bit about sort of the nitty-gritty of the actual protocol. So using the equipment that we have in the lab, you would want to set up your stir plate in this way. The first thing is you got to make sure that if your hot plate is setting its temperature based on the thermocouple must be somehow in contact with the surface of the hot plate. We usually use these aluminum blocks to make that connection. If this thermocouple isn't touching the hot plate and you have it set to some temperature, it will just get hotter and hotter and hotter because it can't sense that it's warming up, right? So you've got to make sure that the thermocouple is in contact with the hot plate. For recrystallization, well, you can just stick it into the aluminum block. Then what you're going to want to do is you're going to want to make your saturated solution. And the way you do that is like this. You're going to get 2 Erlenmeyer flasks, and you're going to put in more solvent than you think you need for the recrystallization into one, and you're going to put in a boiling stick. Have you used boiling sticks before? Boiling sticks are absolutely essential for good recrystallization. These sticks will nucleate the bubbles in the solvent that you're using so they don't get overheated, superheated, and then when you stick your pipette in, they boil all over the place and they can start a fire and burn you, depending on the solvent. So the first thing you do is you get pure solvent, that perfect solvent you picked, and you put it on the hot plate and you set it at a temperature that solvent will boil. So let's imagine we have that solvent now gently boiling, and this stick is causing the bubbles to nucleate, so you get a gentle boil. Then what you're going to do is you're going to take your crude material and put it in a second Erlenmeyer flask. And we don't want to put this compound without solvent on it onto the hot plate directly, because there's no solvent on there, and so the hot plate surface is actually very, very hot, and you could actually burn the compound before there's any solvent on it. You want it to be dissolved at least a little bit before it goes in there, and you want there to be some solvent present in there. So the best way to do it is to put your solid in an Erlenmeyer flask and then use a pipette to transfer some of that boiling solvent into the solid. Okay, so I'm transferring it, and I'm swirling it around. And in here is going to be a little bit of solvent and a lot of solid initially, right? It's hot solvent, so it might start dissolving, but we've only added just a little bit of solvent, right? So it's not fully dissolved yet. We haven't made that super saturated solution. Once there's a visible amount of solvent in there, now you can put that Erlenmeyer onto the hot plate, and it's going to start to boil. Once it's boiled and there's still solid there, you know you haven't reached supersaturation yet because there's still solid there. You want it all to be a solution. You want all the solid to go away. So then what you do is you simply transfer boiling solvent, add a little bit, and watch it. And you want a boiling stick in this one too, so that the bubbles have something to nucleate on. You'll transfer solvent. Each time you transfer, swirl it around, wait till it boils again. Once it's boiling, if there's still solid, you haven't gotten there yet. Right? You're going to want to make sure that all the solid is gone. So you keep transferring, and there's usually a moment when the solvent in there goes from a really cloudy to a nice clear, it's sometimes colored, but it's clear solution. And it usually happens with just a couple of drips. Once you're there, you've hit the optimal point, and without hesitation, you should move this flask off, pull the boiling stick out, and allow the supersaturated solution to start to cool. Okay? Slow cooling is better than fast cooling. So some people actually like to put a towel on the bench because the bench tends to be cold. If you put a towel on the bench, it will insulate the flask a little bit, and the temperature will go down. It will go down more slowly. The reason why is what we're hoping to happen is have these perfect crystals of something form. And we want to give the solution plenty of time to slowly layer that crystal, layer upon layer, a pure compound. If you crash it out too fast, say you stuck it in ice, for example, everything would crash out all at once, A and B and everything, right? So we don't want to rapidly cool it because then we're not going to affect the purification. We're actually just going to precipitate. That's the difference between recrystallizing and precipitation. You just precipitate everything out and then it's not pure, right? So slow cooling tends to be the best, all right? So then after that, once it's at room temperature, or once you see a substantial amount of solid there, right, then you almost always have to break up the crystals. Usually it forms kind of a layer along the bottom, so take a spatula, break them up, and then swirl it and use a vacuum filtration to isolate. Okay? So that's the general technique.